Okay, so good evening once again. We'll start with where we stopped last time. Okay, in the previous class, yeah. So in the previous class, we were discussing about what is object tracking. Okay, and we also discussed that there are two broad types of object tracking, that is tracking by detection and tracking by matching. So what is object detection or what is object tracking? Okay, so tracking basically means, let's say you are given a video sequence as an input, okay, and we want to, in that video sequence, let's say there is an object, okay, which is moving, and your aim is to try to find out what is the movement of the object, or what is the path in which the object is moving, right? So the video sequence that we are considering, you can consider that as a set of successive frames, image frames, as a set of images which are stacked together in the temporal axis. You can consider it as image frames, and various processing is done, okay, within those image frames. And so we were discussing about tracking by detection specifically, right? So in tracking by detection, what is done is, as you see in this particular figure over here, let's say you have an image frame. Okay, this is the temporal axis over here, and this is basically the video sequence that is there. Okay, so in the first frame, if we can build a detector, an object detector that can detect the object with a high accuracy or a high precision and reliability. Okay, so if you are able to, if the detector is able to detect the object properly, then this can be, the detector can be used for detecting the presence of the object on all the frames, okay, or all the individual frames. So each time it detects the object, it is able to find out what is the position of the object, right? So once these detector output responses are obtained for each of the frames, then what can be done is we can kind of just link all that together in order to get the trajectory or the path in which the object is moving. Okay, now there may be a case where the object may enter or leave the frame. Okay, so let's say the object is subsequently, after some time, the object has left the frame. So what happens is, if the object has left the frame and the algorithm is not able to track that particular object again, then what it can do is it can just stop the particular trajectory over there, okay, and then it keeps on looking again in all of these successive frames, and the moment the image or the object comes back to the image, okay, if you're able to if the algorithm is able to detect it again, then again a new track will start. Okay, so this is how the tracking by detection algorithm or tracking by detection method works. Okay. So next what we will see is, so in the previous case it was you had just one object, okay, as you see over here, right? There was only one object in each of the image frame, and the detector can be used to detect this object, okay, and you're assuming that the background is kind of fairly fairly uniform, and there are not many other objects within, in the sense the object that has to be detected is different in appearance as compared to the background. So these are some of the assumptions that we make, and so making these assumptions and also building a very good powerful detector, what we are doing is, for each of the frames we try to find the detector response, and we just kind of link them together to find the trajectory or the path in which the object is moving. Okay, so this is a case when you have only one single object. Now, what if you have multiple objects in the video sequence? Let's say it is not just one single object that you want to track. Let's say you have multiple objects. Okay, so in this case, let us just consider there are two different objects. This is one object and this is another object. Okay, and the algorithm has to track both the objects. Okay, in the video sequence. So in such a case, something which is as simple as this doesn't work, right? What we need to do is we will have to put some more improvement in the technique, maybe some more constraints in order to make this better. So we'll just see what we can do. Okay. Now in this figure over here, we see that there are two objects to be tracked, right? So let us say in this first frame over here, okay, let us say that the detector is able to detect these two objects. So it is able to detect this particular object as well as it is able to detect this particular object, let us assume, okay? Now what happens is, now in the second frame, if you are observing, what you'll see is that this object 2 is still present in the frame, okay, but object 1 is nowhere to be seen, right? So this is a case wherein the object has left the frame, right? And then if you look at the next in the third frame, what happens is this object 1 has come back again over here, okay, and object 2 is still present here, right? So there may be instances where the one of the objects may leave the frame at one particular time and may come back at another particular time. So when you are working with a good object tracking algorithm, what is expected is that although the object is leaving the frame and coming back, it should still be able to detect the object and continue with the tracking. Okay. Now here, so in the case of multiple object detection or tracking, okay, so let's leave the case of detection. Let's say that we do have a detector output which is well. Please mute. Okay. Yeah, so continuing with the object tracking. So what we were discussing was for multiple object tracking. So if you have multiple objects within a video sequence, and you want to track all the objects which are present in the video sequence, okay. Now what can be the challenge here is that, okay, when you have this object detection output, okay, will it be able to track this particular, let's say track 1 is a track for this object 1, okay, and let's say track 2 is a track for object 2. So in that case, will the algorithm be able to track this track 1 as well as this track 2 properly? Is that would be the challenge that we will be having, right? So how do we know, or how can we say that the response, so let's say you're taking another frame, okay, and the response that we get, should this response be belonging to track 1 or track 2? How can we say that? Okay, or these are some questions we're going to just see later. That is, how will it be able, once you have the detector output, how will it be able to say that this particular response belongs to this particular track or not? Okay, so when you have multiple objects, the challenge becomes even greater when you have to be able to correctly identify which is the track which belongs to each of the response. So, so in order to allocate, okay, the detects to the tracks, what we do is we give a particular charge or cost for the allocations. Now, what that means is we, in order to allocate the fact that a particular response that we got, okay, is belonging to, whether it is belonging to track 1 or to track 2, in order to identify that, we give some kind of a cost function, okay. Now what kind of cost function, that we'll see later, okay. So let us say that the cost functions that we are assuming, okay, let us say that for this particular response, let's say this is the response that I'm considering, okay. So for this particular response, I'm saying that the cost function for that, okay, the cost function value for that is C11, okay, that is for the detector output response 1, okay, being allocated to track 1. And let's say the cost function that this response belongs to track 2, Okay, let me assume that it can be denoted by C12. So C12 means it is the cost allocated, okay, for allocating the first response to track 2, and C11 is for allocating the first response to track 1. So given these cost functions, okay, what we do is, so if we observe in this particular figure, we can easily say that this C12 cost function, it's going to be a high value. In the sense, if you just try to see this output response, okay, visually if you are trying to see, we can say that this is for track 1, and for the subsequent frames also, when you have objects over here, you can say it's all belonging to track 1, right? So we formulate the cost function or the calculation of the cost function in such a way that, okay, this cost function would be maximum for an unlikely track. Okay, so the when you're trying to allocate a particular detector response to an unlikely track or the track in which it may not be belonging, you see that the cost function also increases over there. Okay. Okay, so now here in this case also, when we see the object has moved from or left from the frame, okay, and in the third case we see that the object has come back to the frame, right? Now, if you just assume these frames over here, one more assumption that we are making here is that the what is it, the different frames which are present in the video sequence, okay, we can say that around 60 to 70 frames are present, okay, within a second. Okay, so what that means is, for the duration which is existing between each of the frames would be around 1 by 70 or 1 by 75, okay, depending upon what is the number of frames per second which is present in the video sequence. Okay, so what that means is that, okay, here it is very unlikely that this particular response, okay, has moved to a very far distance in the next frame, okay, as compared to some other response, let us say, which is near to it. Okay, so what we are assuming here is that we are assuming a slow moving object. Slow moving in the sense, we are assuming that it may not travel a very long distance, okay, or it may not go a very long distance far apart from its initial position when we are looking at the next frame. Okay, so that is one assumption. And as I said earlier, this cost function C12, okay, it will have a high value because the response is located much further away from the track 2. Okay, so this is basically the track 2, right? And if you look at cost C11, okay, if you're trying to track for all the subsequent responses over here, okay, what happens is, since it is C11 will be having a lower value, and we can also visually see that it is closer to track 1. So here the assumption that we make is that the object has not moved too far, or too far away from the initial frame or the previous frame which we are considering. And accordingly, when you are formulating the cost function, we'll see how it is being formulated, right? The higher the cost function value here, it means that the less likely it is belonging to that particular track, or the lower the value of C11, or whichever is the cost function that we are considering here. Okay, we can say that lower the value, the higher the probability that it belongs to track 1 or the track corresponding to it. Okay, so coming to here now, as we discussed over here, there is we are assigning a particular charge function or cost function for allocating or detecting the tracks, right? Now, what is this particular charge or the cost function that we are assigning? Okay, so that is one thing we have to look at, and also the fact that there are many assumptions that we are making. Okay, what are the different assumptions? So in this case, what we assume is, as I said, we are assuming that it is a slow moving object. Okay, now, and some examples can be, let's say, a person who is walking, or let's say if it is some kind of a match which is going on, probably a ball which is moving during the match, and so on. Okay, so in these cases, what we are assuming is that the object does not move very quickly between each frame. Okay, considering the fact that each the duration of each frame, or between each frame, may be just 1 by 70th or 75th of a second. That's it. Now, another assumption which we make here is that, as I said earlier, the appearance of the object, it remains the same between each frame. So if you're just assuming here, let's say you have a frame here and you have another frame here, and you had an object detected here and you have an object detected here, we are also assuming that since it is the same object, right, the appearance would not have changed much. Okay, there might be some kind of an illumination variation slightly, but what we are assuming is that the appearance over here, okay, it remains the same, or it remains very similar between each of the frames. And when I say appearance, what that means is it could be the gray level intensities, okay, or the pixel intensities. It can be the color information. Okay, that's what you mean by the appearance. And if we are able to match the appearances of the detector responses, right, then that means we can allocate the cost to the tracks also. So by looking at the appearance also, we can kind of conclude that, okay, so these belong to the same object, okay, and then do the tracking. Now, another point you have here is, how do you decide whether the cost which we have allocated, okay, whether it is a high cost or low cost? Okay, how do you decide between what should be the threshold for calculating what is the cost function, or how low or how high is the should the cost be? Okay, and also how to decide which is close distance or which is far distance, okay, in terms of the similarity. So these are other issues or other concerns that we have when we are trying to develop the algorithm. And then finally, so how to use these distance. Now, what we see is that basically it is depending upon what is the kind of application that we are using, what is the kind of frame rate that is present in the video, what is the image resolution which is present in the video, and so on. Okay, so this method of tracking by detection, it works only if you have a strong, reliable detector, okay, that is able to detect the responses in each of the frames. And then what you do is you basically just try to connect them together to form the path. Okay, so that is a basic working principle of tracking by detection. Okay. Now, let's just look at some examples of how the tracking by detection can work. So let's say you have some kind of a room or a corridor or something, and there is a CCTV camera which is kept over here, and it is continuously recording all the videos, let's say, and let's assume that there are people moving around within the corridor or within the room where the CCTV camera has the view, and so on. Okay, so in this case, let's say what you're trying to do is trying to see how the people are, what is the trajectory of the people or the path of the movement of the people, or so on. Okay, so the input for the algorithm that you're giving would be the video sequence which is given from the CCTV camera. And the output which you have obtained would be what is the trajectory or the path of the people who are moving. It could be people who are moving, it could be one person of interest who's moving, and an object of interest who is moving, or so on. Okay, so in this case, what we assume is that, okay, we go with something which is known as background subtraction. So before coming to that, what we assume here is that the background which is present over in the particular video, okay, it is constant and that it doesn't change. Okay, so in the case of the CCTV camera, the surrounding background will remain the same. It's just that the objects are moving around, right? So the assumption that we make is that we know what is the background, okay, and the background should be uniform, or it should be constant between different frames, and also that the objects which are present should look different from the background, okay, in terms of the appearance, that is the gray level intensities or the color hues and so on. It should be an object that should look different from the background. So in such cases, if you are making all these assumptions, okay, in such cases we can go with a method which is called as background subtraction. Okay, so what does that mean is, so let's say you have a particular frame. I'm considering a particular frame, and let me assume that this is the object that needs to be what is it, tracked. Okay, and let's say this white color what you have is the background, right? So this object that needs to be tracked is what you call as a foreground. Foreground means the object of interest that we have, and anything which is other than this object of interest or other than the foreground can be called as the background. Okay, so in background subtraction, what is done is, assuming that you know what is the background, okay, you kind of just as the name says, you try to subtract the background from each of the frames. Okay, so by doing that, what we do, what happens is, what we are left off with is only the object of interest or the foreground, which is the one that we have to track, right? So once that is obtained, we can easily go ahead with joining or finding the trajectory for that. So when you're going ahead with background subtraction, okay, now this background subtraction method, it can also be called as, it is basically an object detector method, because you're trying to, by subtracting the background, what you're trying to do is you're trying to detect where the object is, right? So what you do is, let's say this is the image that you have, this is the foreground or the object of interest, and let us assume that this is the background. Okay, now in this case, this particular here what you have is the image frame. Okay, now let us assume that the background is already known to us. So if the background is already known to us, this is a background. What happens is, in the background subtraction technique, this background which is known to us, or in some cases it is being estimated if it is known to us. Let us assume that this is known to us, and when we subtract this background from this image, what we get is, basically what we are left out with is only the foreground object that you have. Okay, so and this is you can call this as the detector response over here, right? Now now if there is only one object over here, okay, it works well and good. Okay, now what if there are multiple objects that needs to be tracked? Okay, so if there are multiple objects, then one information that we can make use of is the appearance of each of the object. Okay, if each of the object has a different appearance, then that information can be incorporated in order for tracking the objects. Okay, so here background subtraction, as I said earlier, background subtraction is as simple as just estimating the background and subtracting from the image in order to get the or detect the object. Okay, it's a very simple method, but again, as I said earlier, it comes with a lot of assumptions. Okay, one assumption being that the background should be constant, right? Now, what if the background is not constant or not fixed? Okay, so in that case, this particular approach will not work, because we are assuming that the background should not change. Okay, so in order to improve this kind of method further, what can be done is, if the background change is it's slightly changing, it's not changing abruptly, but let's say that the background is changing slightly, then we can, for this particular background which has been estimated or which is known to us, we can accordingly make the small changes in this background when you're trying to or before doing the background subtraction. Okay, so it's all about estimating the background or updating the background if in case the background seems to change slightly, and then going ahead with the background subtraction. Okay. And then again, let's say you have people in large view, okay, or let's say if you have people who are stationary for a very long time, or if there are two people who are close together. In all these cases, you see that the background subtraction, okay, will not really work very well. Okay, so there are a lot of assumptions or constraints when you're using the background subtraction technique, but it's a very simple tool in which you can easily detect what is the object. Okay, so let's just try to summarize this. So here, as we said earlier, what we do is we try to create a detector, or we try to build a detector which is able to detect the object in all the frames. So if you have multiple frames like this, okay, this detector should be able to identify the object in all the frames. And after identifying the object, okay, what I've been saying till now was these all positions or whatever information is obtained from the detector output response is kind of linked together or joined together to to form the trajectory, right? Now, how exactly is it done? Okay. So in the first frame, the detector will detect all the object, and in the nth frame means after the first frame, any other frames that come, okay, beyond that. So in the nth frame, there are three steps which are followed, which is link, spawn, and reap. Okay. So link means we will associate the detector response with a particular track. So if you have a particular track, let's say track 1 over here, and you have a response, okay, we can allocate this particular response to the track with the help of some kind of a cost function, right? So that method is known as link. Now next is spawn. So spawn means suppose that we have a detector response, okay, and this, let's say I have a detector response here, and I'm not able to link this particular detector response with any of the responses in the previous frame. Okay, so in such a case where the detector response cannot be associated with any existing track, then what that means is this is a new object that has come into the frame. Okay, this is a new object which was not present in the previous frame and has just come to the frame here. Okay, so what is done is, in such a case, when you are detecting a new object, then the tracking would start from here. So from here, this object is also one among the objects that has to be tracked, right? So that process is called as where you're identifying the objects which are coming and then tracking them. Okay, that is called as spawn. And the third method over here is called reap. Okay, now reap means suppose that you have a very let us consider that we are assuming a few frames over here, and the track doesn't have an associated response. Okay, then that means that the object must have left the frame. There is no response, right? So it is just the opposite with the spawn, where in the spawn the object has entered and you detected a new object and you're trying to track it. In the case of reap, it would be just the opposite. Okay, so where you have a track, okay, but you do not have any associated response with that, which means that the object must have left the frame. So in such a case, if you have identified that the object has left the frame, then you need not keep tracking it, right? So it will stop the tracking over there. So it will keep tracking as long as the object is present within the frames. Okay. So this is how the tracking by detection works. Now, do you have any doubts till now? Okay, moving ahead, let's go to the second type of tracking, which are the second category, broad category of tracking, which is basically tracking by matching. Okay, so first one was the tracking by detection. So in tracking by matching, Okay. In the case of detection, what you're doing is you're trying to detect the particular image or the object which is present, right? In the case of tracking by matching, you're not trying to detect the different parts of the object as such or per se. Okay. So here what we are doing is we are assuming that the person that you want to track. So let's say this is a particular this is one frame of the video sequence, and this yellow box, the person in yellow box is the person whom we are interested to track, and this is just a zoomed version of that. Okay. So here, let us assume that we want to track this particular person who's playing, right? Now, what we observe here is that when you're comparing this person, or the if this is called as a bounding box, that is just bounding this particular object. In this case, it's a person, right? So if you look at the person and compare that with the whole image dimension, what you see is that the person is actually quite small. Okay, just it's just very small patch as compared to the whole image, which means that the information that is present, okay, with regard to the object that has to be tracked is very small. So let's say it is maybe just 10 to 30 pixels, okay, for the bounding box over here. Okay, so in here what we see in this example, as I said earlier, is that the person is too small, and that's why it's called as a 30 pixel man, for this particular case. Okay, let's leave that. So what we assume is that the frame rate is 30 hertz. Okay, so if the frame rate is 30 hertz, what that means is you'll have 30 frames per second, or 30 images per second, right? Now, in such a case, it is difficult to identify. Now, if you look at this particular image, it is very difficult to identify which are the hands of the person or which are the legs of the person, or so on. Okay, so if you're using just a normal object detector in this case, okay, the accuracy or the accuracy with which it is able to detect such an image would be difficult, because as I said earlier, the amount of information that we have here is lesser, right? So when we are usually, if you are trying to capture the movement of a person, what we'll do is we'll look at the information of the leg positions of the leg, okay, the movement of the hands, or what is the position of the hands, and so on, right? So instead, in this case, where you're tracking by matching, because of these limitations, what we are doing is, instead of tracking the person or the different parts of a person, okay, what we do is we will track this bounding box. So you have this bounding box which has bounded the object, and what we do here is we try to track the bounding box here instead of trying to track the person, person or the parts of the person. Okay. So by this, what we are doing is, now when we are trying to use the bounding box, what we are doing is we are basically looking at the matching similarity of each of the bounding box with respect to the successive image frames that you are having. So here, this particular method, okay, you can also call it as the image stabilization. Okay, image stabilization, where what you're trying to do is basically you're trying to track the bounding box instead of the person, right? Now, in image stabilization, what we are assuming is that the bounding box which is present in the middle of an image. So what we assume is that if this is the bounding box of the object that has to be tracked, okay, it is present somewhere very close to the center of the image. Is one assumption which is made in the image stabilization process. Okay, so we assume that the bounding box is present somewhere in the center or in the middle of the image. And instead of tracking the movement of the bounding box as such, okay, what we do is we just try to, you're just trying to change the background. Okay, in the sense, if you go in detail over here, what you're trying to do is you're trying to basically look for the neighborhood or the background and see or look out for similar patches. We'll see the details later. So what we are assuming here, as I said earlier, is we are the image transformations, okay, which is present. It would keep changing according to what is the motion information that we receive from the object, right? So what we say is that this particular bounding box, okay, is kind of stabilized at the center of the image, okay, and only the neighborhood or the neighboring regions keep changing. Okay. Just give me a minute. Okay, we'll continue. Okay, so next what we'll see is we'll see how to track the box in the video. Okay, what is the step by step or what is the basic idea over here, right? So what we are assuming here is that the transformation, okay, or what is the change between each of the frames, it is only a translational transformation is the assumption that we are making, okay. That is, if you are looking at this particular image, okay, what you are trying to assume is that this particular bounding box, the transformation that has happened is only a translational operation. It can be along the x-axis, along the y-axis, it could be along both the axes, some measure of tx and ty, right? So here the assumption that we make is this particular bounding box which is present in this video frame or the image frame, okay. Now this bounding box, if you are comparing with the next frame, the only transformation that you have is only the translational transformation. So when you are assuming that, what happens is that it will make the computations, everything much more simpler, okay. So in this particular figure that you're considering, okay, let's say this is the this yellow bounding box is the one that we are trying to track, okay. Now what we are assuming, as I said earlier, is that we're just assuming it is undergoing only a translational transformation, okay, when we are trying to compare with the successive frames, okay. And what we are trying to do here is, since we know it is a translation operation, we are trying to find out what is the transformation, what is the translational transformation that has happened, okay, in order to get the positions of the new positions of the object or the bounding box. In this case, it's not the object alone, but it is the whole of the bounding box. So for that case, what is done is we take a particular neighborhood around this particular bounding box or the object that the bounding box that has to be tracked, okay. And we consider multiple such small bounding box patches, okay, which is of the same size as this one, right? And after and this is done for each subsequent frames, right? So let's say in this particular frame I have this bounding box. In the next frame, in along that particular neighborhood, okay, I assume different other bounding box patches, and then I will compute what is the similarity between each of those patches with the original patch which is present in the current frame, okay. So basically what you're trying to do is you're trying to match the similarity between each of these image patches or each of these boxes, and the box or the image patch which has got the maximum similarity would be would be the selected as the one in which the track is moving, okay, or the point in which the track lies, okay, and so on. So what we're trying to do is we consider a neighborhood and we consider multiple boxes of the same size within that neighborhood, and then we try to calculate how much is the similarity measure of each of that. And what we will see is that if you get an image patch which is very highly similar, then you can say that this person has basically moved to or the translation operation, okay, or the translation transformation which has happened, okay, because of which the person has moved from so and so position to the other position, right? So here, since we are trying to find out which is the box within the neighborhood which has got the maximum similarity, this particular method is called as tracking by matching. Okay. So again, as I said earlier, what we are assuming is that the object has not moved very fast between each frame. Okay, it is a slow moving object. Only then it would work well, because what we're considering is only the neighborhood and we are not taking in the whole image, right? Okay. So now let us say what could be a good test for the similarity. Okay, so for testing the similarity of two patches, let's say this is one patch in one particular frame, you have one patch, and in the subsequent frame, let's say you have another patch, right? And what you're trying to do is we are trying to see how similar, and these two are of the same size, right? We are trying to see how similar these two patches are. So in order to find a measure for this similarity, okay, we can make use of SSD. Okay, SSD stands for sum of square differences, a term which we have already seen earlier in one of the lecture classes, right? So SSD stands for sum of squared distances, which means, as you see over here, right? In one particular patch, this is one particular patch in the nth frame, and this is another patch in the n plus 1th frame, and we are assuming that these patches are near to each other, right? So here in this case, what happens is we are calculating the sum of square differences. How is it calculated? We take the difference, we square that difference, and we just take the average of that. Okay, so this is the expression for the sum of squared differences. And using this SSD function, what we can do is we can try to find out how much is the similarity. Okay, so when you're considering the neighborhood, we can assume that the position of the yellow bounding box, it has not moved too fast in the next frame, right? So what we are basically doing is we are bounding the neighborhood by velocity constraints, okay? Because what we are looking for are similar boxes, and we are assuming that that is very near to the the actual yellow box which is present, right? So that means you're trying to kind of bound the neighborhood, or you're trying to bound by the velocity constraints. So how that helps is, now in that case we need not go for searching the whole of the next image frame, right? So you can just bound that within particular velocity constraints and look only within that particular neighborhood. So another way we can improve this method, that is the tracking by matching method which was discussed right now, is by using the Gaussian pyramid. Okay, so in the Gaussian pyramid, if you remember, right, you have a particular image, a high resolution image, and then you keep reducing the resolution. Okay, and as you keep reducing the resolution, you can give a particular hierarchy to the different images which are present. So it's all belonging to the same image, it's just that the resolutions are varying, right? So this kind of a structure which has been constructed, which can be constructed, is what you call as the Gaussian pyramid. Okay, So what we're doing here is, in order to improve the method, we can make use of the Gaussian pyramid. And here what you're doing is, instead of searching the neighborhood of the original frame, we can look for similar boxes in the neighborhood, of the lower resolution, right? So instead of going for different frames over here, you can just take the depth response over here, right? And you can look for what are the similar patches which are present, but in something consequent frames where the it is kind of scaled down, okay, and it is not having exactly the same dimensions as before. So how that helps is, when you're having a Gaussian pyramid like that, and when you are having an object data to work on such the Gaussian pyramid like images where it is of a different resolution, how that helps is that it brings about invariability in the scale. Okay, that means even if the object is big or small, okay, it would still be able to capture what is the detailed information, right? So the algorithm which we are designing, okay, it will be independent of the size of the person or the object which is present with it, right? So that is the advantage of using a Gaussian pyramid along with velocity constraints for the neighborhood. Okay, so that's about the tracking by matching. Now let us look at this mathematical equation that you see here, right? Now PT indicates, okay, what is the index of the patch that we are considering. So T refers to the teeth frame, okay, and we are assuming that the patch or that yellow bounding box is basically this particular variable PT, okay, and this one here, IXT, is basically the image which corresponds to the teeth frame. So this one can also be written as I of x comma y comma t. Okay, just to make it clearer, because this I of xy is basically the image and t is the corresponding teeth frame. Okay. Now, what we are assuming here is that the patch, okay, it is at a distance xt in the nth frame, okay. So when after translation operation or the after translational transformation, what happens is, from xt it has moved to another location which is x plus h, okay, and you have a teeth frame, right, and the next frame that we are considering is the t plus 1th frame, right? So after translation operation, the patch has moved to x plus h location, right, which is present in the t plus 1th frame. And in order to calculate, okay, over here what is done is, again it is the SSD equation. SSD was standing for the sum of square difference, okay, that itself is used over here. The only thing is notations are different, okay, the notations being that here you have I of u comma t, here you have u plus h because you have this translation vector, okay, and for the t plus 1th frame, okay. So what you're doing is, you're considering two patches, okay, one patch here, another patch within the neighborhood of the next frame, okay, and then we are trying to see how similar these two patches are. So we take the sum of squared distance over here. Okay, now going further, okay, so going further, so what we want to do is, we want to find out the minimum of this SSD error, right? So we are trying to minimize the cost function in this case. So in order to minimize the cost function or minimize a particular equation, what we do is, we basically differentiate that and then equate to 0, right? So in this case, you can differentiate it with respect to the variable h, okay, which is the translational transformation which has to be found, right? So I can write this as del h e of h is equal to 0, where this del h means that it is a differentiation with respect to h, okay. Now, if this value h is small, I can rewrite this particular equation I of u plus h comma t plus 1 is equal to, I can write it as I of ut plus h transform delta I. Now, delta I here refers to the image gradient. Okay, just note that the delta I is basically nothing but the image gradient. Okay, and if the value of h is small, okay, we can just simplify the equation which is given over here, right? We can write it as I of u plus h t plus 1 is equal to I of ut plus h transpose delta I. So what we do is, now that we have got this particular equation for I of u plus h t plus 1, right? We can just substitute this particular equation in over here. Okay, just substitute this in this here. Okay, just substitute it over here, and you can then try to simplify. Okay, so what we do is, as I said earlier, we differentiate with respect to h, and we try to simplify that. So after substituting and rearranging, let's say the equation which you have got looks somewhat like this. Okay, that is delta u. Here you have sigma u. Here you have delta I and delta I transpose into h, which is basically my translation vector which I have to find out, is equal to sigma u. You have I of ut minus I of ut plus 1 delta I. So this is the particular equation that needs to be simplified in order to find out what is, or estimate what is a translational transformation, because that is exactly what we're trying to do, right? Trying to find out what is the translation. Only if we know what is the translation can we find out other attributes with regard to that. Now, if you look at this particular, let's say this particular right hand side over here, what we see is you do not have a u plus h term here. You just have I of ut. Okay, that is the original, image that you have with the teeth frame, and here what you have is I of u t plus 1, and then it is multiplied with a gradient image. Okay. Now, coming to the left hand side over here, okay, now this particular equation, delta I into delta I of transpose, this one can be written this way. So I can write delta I into delta I of transpose, okay, this is equal to writing sigma I by, dou I by dou x, dou I by dou y, and I can write here also dou x, dou I by dou x, and dou I by dou y, right? And what is done is, it is basically you're trying to multiply these and form the matrix. So how I got this is basically from here, the left hand side, right? Now this can be equated to, when you're trying to open the brackets, I can write this as dou I by dou x, dou I by dou x. Okay, here it's going to be dou I by dou x, here it's going to be dou I by dou y. Now here again you have dou I by dou x, dou I by dou y, and here I have dou I by dou y, dou I by dou y. So this is the matrix form, okay, of what has been represented over here, right? Now, if you look at this particular image, what we see is that all these elements which are present here are basically just the gradient functions, right? I have dou I by dou x, dou I by dou x here. I have dou I by dou y, dou I by dou y over here. So all the elements particularly present in this particular matrix 2 cross 2 matrix are, they are all the gradient information which we have obtained from the the image. So when we are trying to substitute, and when you are getting this particular equation, so let's say the particular value associated with this, when you're solving this particular matrix, okay, the value, if you're getting a very small value, then very small in the sense, let's say it's zero point 0.1 or zero point 0.5 or zero point 0.01 or so on. Okay, then what that means is we can solve this equation, as a linear, as a system of linear equations. We can solve it for h. Okay, but when we are solving that, what happens is the right hand side will be very high. Okay, the value would be very high, and we also would see that in such cases, the algorithm that we are using or that we are developing will also be not reliable. So what we do is, what we are saying here is this particular value of the matrix, okay, this particular matrix value, it should not be very small, because if it is too small, then the value of h also becomes too high, and therefore it is not a reliable measure. So instead, what we can do is, instead of directly trying to calculate these matrices over here, right, or the matrix value over here, what we can do is we can just try to find out what is the eigenvectors or the eigenvalues, right? So if the eigenvalues are very small, we can say that the solution is not reliable. Okay. So in this particular matrix, as I said, what you have is basically the gradient information, right? And what that means is, let's say if you're having the matrix value very small, right? Then in that case, it means that there is no gradient in that particular patch. And if a patch, let's say, has a person in it, then that means that it is highly probable that whatever is the gradient that you're getting is basically the matched case. So if I just try to interpret the above thing with respect to this particular image over here, right? So here what we are trying to say is that we are considering all these different patches, right? We are considering all these different patches. And what we assume is that when we are trying to find the gradient over here, if you have a uniform background, then in such cases, there won't be any gradient information which is present. Okay, and the only patch in which you will have some gradient information would be the kind of, that would be the similar box. Okay, when it comes to comparing this yellow box over here, the best matching or the highest matching boxes, okay, with respect to the initial yellow box, would definitely have have a high value for the similarity. Okay. Okay, so this particular method, which was discussed now, okay, was proposed by Shi and Tomasi, 1994. Okay, just note this down. Shi and Tomasi in 1994, and in one of their papers, they have elaborated on this particular method and what are the different results that they've obtained. So let's take this particular result, which has been taken from their paper, right? So the name of the paper is given over here. Okay, so in their study, what they have done is, as you see in this particular figure, what is done is, if you're looking at this particular figure 1, okay, it is basically an input image, right? And here the paper is trying to see what are some of the points or some of the features that can be considered good enough for tracking. Okay, so while you're tracking, that is the basic idea, is while you're tracking, trying to track a particular object, maybe not all the points which are present in the object needs to be tracked. Okay, there may be some points of interest which are present in the images which are sufficient to be tracked. You need not go with the whole thing. So that helps with the computational complexity also. So for example, if you have this particular image, okay, this is the output with which the authors have got after detecting interest points or the key points. Okay, and here all these points that you see, right, these basically indicate those points with the highest information with regard to how the tracking, how the movement would be taking place, right? So instead of going for any 2 points in order to find out what is the tracking by matching over here, you can just instead of assuming all the points or considering all the points, you can just take those points which are present the edges. Okay, if you take for example in this particular example over here, as well as this particular example, what we see is that the interest points, that is those points where it has maximum information regarding the movement and the tracking and the matching, right? So these particular points are usually present either on the corners of the object, or it is present along the edges of the object. Okay, so that means when you are taking the gradient information, that itself will give you a very good description about how the object is. So in this figure 2, what we are seeing here is basically image with features that are good enough for tracking. So we are saying that instead of looking at all the points, we are just looking at these points and we are saying that it is good for tracking. Okay. And these points, as I said earlier, it is mainly located along the corners and the edges. Now, if you're looking at this third figure, now just have a look at this. What it is basically trying to plot is the dissimilarity measure, and along with each frame. Okay, dissimilarity, or you can just take it as a cost function over here, which is basically SSD, right? The sum of squared difference. So when you're trying to plot that dissimilarity function, the cost function, with respect to each frame, in this particular figure, what we see is that initially it kind of was able to track well, because the values of SST were small. And as I said earlier, the value of SSD, or the error that you're getting, the better would be the algorithm that you have developed, right? So here what we see is that in the initial cases, it was more or less it is within a particular tolerant level, and it is not too much of error, right? But at some point after a few frames, what has happened is that the error starts to increase. Okay, there is some kind of error that has happened, right? And because of which, what happens is in the subsequent frames, okay, that error gets propagated, and it goes like this, right? So here this is just an example of how we can use the interest points in order for tracking, and how the tracking is done. And as I said, when you're trying to look at the SSD plot with respect to the frame, what we are observing is that, let's say at some point there has been some error in which the SSD value started giving a high value. So if the SSD value keeps starting to give you a high value, means that the object is now no longer being tracked properly, right? And there is some error function over there. Okay, so this is when you are assuming a translation transformation between each frames. Now, instead of just assuming a translation transformation, we can also go with a pre-processing technique where you try to also incorporate the affine transformations. Okay, so what that means is, in the previous step, what we have obtained is or what we are assuming is that the only translation operation has happened, right? That is, from frame n to frame n plus 1, between these two consecutive frames, we are assuming that the only transformation that has obtained is translation. And then we have seen the formula in the previous slide where it just describes this, right? Now here we can improve the method further, okay, by assuming, or by saying that, or assuming that, if you're comparing frame 1 of the video sequence with any frame n plus 1, right? The translation or the transformation which is present between these frames, which is kind of a little time apart, okay, here the transformation is not just translational, okay, but it is an affine transformation. So this is the assumption that we are making, or this is the post processing step that we are doing. Okay, so I'll just repeat that. What we are doing here is In the previous case, we have already seen the case of where you're trying to assume that it's a translation operation, right? And in order to improve the previous method, okay, in order to improve the results that we obtain from the translation operation or translation motion, right, what we are doing is we can also add in a post processing step, right, by assuming that there is an affine transformation which is present between the first frame and the frame under consideration, right? Okay, so let's say that we have estimated the value of the transformation matrix, which is basically H, right? Now we want to confirm whether this particular value H which we have obtained is right or not, or whatever is the translation operation is obtained, if it is right or not. Okay, so we're just trying to estimate that value. So here, along with the assumption that the transformation between the frame is translational, we also assume that there is an affine transformation, and the corresponding equation that we see is shown here. That is, we assume that E is equal to, now this is again another form of the SSD function, or the a sum of squared function. But here the only difference is that now in this case we are assuming the first frame. So we are saying that uh, when comparing frame 1 to frame n plus 1, right? Comparing this, here it is an affine transformation. So here what we are doing is we are taking the first frame, okay? And in the cost function, we are subtracting all the other affine responses that we have, and then we are trying to minimize that. Okay, so here what we say is when we are using affine transformation as a post processing technique, we'll see that the graph of the SSD, or the dissimilarity function, would would be better. Okay, just to give you an example over here, let us consider these two images. If you have noticed, this is the same image that we had discussed in the earlier case, where we said that the track, once it is lost, it is just lost over there and it keeps on going, right? So the error keeps on propagating. If the error has occurred at some initial frames, then that keeps getting propagated. So that is one challenge over here, or one problem here, right? When you are assuming only translation. So this particular graph refers to translation transformation. Now, this graph over here, the bottom one, is basically when you are assuming an affine transformation, right? So when you're doing an affine transformation, here this particular scale is much lower than this particular scale that you're having. Okay, so if you're just trying to quantitatively look at that. Here this is not exactly the same size, okay, because it is kind of a scaled version. So if you take it as the same scale of this one, what we'll see is when you're also adding an affine transformation, it helps with the tracking process, okay, as compared to using only the translation operation. Along with using an affine transformation as a post-processing technique, it will help to further improve the results, as as shown in this particular graph. Okay, I guess we have some more time. Okay, so here just trying to summarize and then I'll finish it off. So, well, what we are summarizing here is that what we do is first we find out all the interest points. So, as said earlier, we need not go about with all the points which are present in the object, but there is only a necessity for looking at the interest points. That is, it could be within the within the corners or the edges and so on, right? So after finding out all the interest points, okay, the next step, or what we then do, is we try to locate all these detected interest points in the next frame, right? And after trying to locate all these detected points in the next frame, okay, you try to match, okay, whether the patch that we are considering, it is matching with the original one or not. If it is matching with the original one, then what we say is, okay, it belongs to the particular track that we are considering. If it is not, then we say that okay, the track has ended. We do not then try to propagate that to the next step. Okay, so if that is not determined, then we just end the track. And if the object which was missing has come back, right, then what we say is that we just start off with a new track in that case. Okay. So previously what we saw was the tracking by or tracking using matching, right? Now there are two advanced methods by which you can do tracking using matching. Okay, the previous one was a very simple approach and it has its own limitations too. Here in this case, it is a little bit more advanced techniques, right? So first one is the summary matching. Okay, so summary matching means instead of just using the SSD scores. So in the previous case, we had been using the SSD scores, which is sum of squared difference, right? And when you're taking a sum of squared difference, it does a pixel to pixel, subtraction kind of. So in summary matching, what is done is instead of just using the SSD or the sum of squared score, we can also use a better summary representation. Okay, like for example, instead of just looking at two patches as such and trying to find out the similarity, maybe you can just find the histogram of these patches and try to maybe extract features from this histogram and then do the matching. So such kind of matching where you're not directly taking the images, but what we are doing is we are making use of a summary representation for such images, right? So that kind of a technique or matching method is what we call as the summary matching. Okay, and another type of method which you have is flow-based matching. Now this flow-based matching is also called as optical flow. Okay, so these two are important and we'll see this in the next class. So for now, I'll just let me look at the time. Okay, I'll just quickly conclude what we have been discussing about in last class as well as today's class. So object tracking, we saw what is object tracking, and in the last class we had just begun with what is tracking using detection. So when you're going for tracking using detection, what it does is we're building a strong detector which can detect the presence of the object in each of the subsequent frames, right? And once the detector output response is obtained, then you kind of just join whatever be the positions which have been obtained, and then you have that as the trajectory. Now in the case of tracking using matching, here in this case, we do not go for a detection of an object as such. Okay, instead we just consider the bounding box of the object of interest for us, right? And then we kind of track how much similarity is there between the patches within the neighborhood. So assuming that what to say the whatever we are considering, right? So when you're using a matching, okay, you also look at different frames and try to look at the subsequent patches within the neighborhood of those frames, and we try to calculate what is the similarity between those frames. And by looking at this similarity measure, we give a cost function to assign it to a particular track if you have multiple objects which are present in that particular video sequence. Okay, and that is how you go about with tracking using matching. And in the case of matching, as I said earlier, we look at only the bounding box and matching the patches. Okay, and we'll go with the different types of matching methods in the next class. Okay, we'll stop here. Do you have any doubts? Okay, the quiz you'll be having today's quiz of two questions for those who are not present here while I was explaining about the quiz. You'll be having quiz two assessments. It would be a continuous assessment from this week onwards. So you will be having for every class you will be assessed with a quiz of consisting of just two questions after every class, and you will have to submit it within 5 minutes. Okay, there are only two questions which are present, and these are MCQ questions. And you can just quickly mark that and submit it within 5 minutes. And the quiz would launch at 5:20. Okay, so till then, if you have any doubts, I can take that.